Okay, so let us begin today's lecture and let us continue with Hamming 7/4 codes. So, here is a Hamming 7/4 code recapitulated in the form of a diagram. So, the original word is S1, S2, S3, S4. So, this is the original word which you need to send. And the code word is the original word augmented by 3 check digits at the end. So, S5, S6, S7, and these will be determined by the following rule, by these sets of equations of these sums being congruent bond 2. And the easy way to remember the sums is the following. So, just look at this diagram. So, S1, so each of these circles corresponds to the 3 equations, okay? And the first equation is S1 plus S3 plus S4 plus S5 is 0. So, this corresponds to equation A, and you just have the sum of all the elements inside the circle A to be 0 mod 2, okay? Congruent to 0 mod 2. Similarly, the second equation involves S6. So, this is corresponding to the circle B, and again the criterion is that the sum of all the elements in circle B must be congruent to 0. Similarly, third equation corresponds to circle C, and the criterion is that the sum of the 4 elements belonging, the sum of the 4 bits belonging to circle C must be congruent to 0 mod 2. Now, congruent to 0 mod 2 means if you just take the usual sum, it's even, right? So, you need, so these, each of these SIs are 0 or 1, and you need the SIs in every circle A, B, and C to sum up to an even number. So, that's the goal. And notice that in any of these circles, 3 of the bits are already known from the given word, and only 1 bit is there which is not known from the given word. But so for each circle you can just find the other bit 0 or 1, so that the sum is even, right. So, this is pretty simple, and that's how you determine the Hamming code word, and we just saw an example of how to determine the Hamming code word. So, of course, we saw how a Hamming code word can detect an error. Here we will also see that in fact a Hamming code word can also correct a 1-bit error. Okay. So, let us check that, let us see why that is true. So, suppose you have a Hamming code word. So, this is the code word which was sent, and there is at most a single bit error. So, there is at most 1 bit where there was an error. So, the single bit error can not only be detected, but also corrected based on the parity checks on the circles A, B, and C. So, here is how you do it. So, notice that if you can find the incorrect bit, because every bit is 0 or 1, as soon as you can identify a particular bit as incorrect, let us say you deduce somehow that S1 is incorrect, then you immediately know what is correct, because you just switch S1 from its current status of 0, 1 to the opposite status. Okay? So, it all boils down to identifying the incorrect bit. So, here is how it works. So, suppose for example that S1 was wrongly transmitted. If S1 is wrongly transmitted, and notice that we are only considering a 1-bit error. So, at most 1 bit can be erroneous, right. So, if S1 is incorrect, then all the other bits must be correct. Okay. So, how are we going to see that from the Hamming code word? Notice that if S1 is incorrect, then for example, if you look at circle A consists of S1, S2, S1, S3, S4, and S5. Among them only S1 is incorrect, everything else is correct. So, if S1, S3, S4 and S5 originally summed up to an even number, which is how a Hamming code word is built. If you just switch the status of S1 from 0 to 1 or 1 to 0, then the sum becomes odd, right? So this circle A, the sum of the elements in circle A will fail the test that the sum of the elements in circle A should be even. Okay? But notice that S1 belongs to all the 3 circles. So the argument that we just did for circle A can be applied to circle B or circle C also. So if S1 is the incorrect bit, each of circle A, circle B and circle C, all the 3 circles will fail the test that the sum of the bits in that circle has to be even or congruent to 0, 1, 2, right? Now suppose S2 is wrong. So let me just actually erase this to clear up. Suppose S2 is wrong. So notice that S2 belongs to exactly 2 circles, B and C. So if you switch the status of S2 from 0 to 1 or 1 to 0, then the sum of the elements in B will switch from even to odd, right? Because in the correct version it was even. That's how a Hamming code word is built. But if you switch S2, all the other things are remaining the same because the error is in just 1 bit. So if you switch the status of S2, the sum which was originally even, because of the mistake, switches from odd to even to odd, right? Similarly, if you switch the status of S2, the sum of the elements in circle C switches from even to odd. So B and C, these 2 circles fail the test that the sum of the bits in a circle, in every circle, must be even. Okay? However, observe that circle A does not involve S2. Circle A, all the bits have been transmitted correctly, and because it's a Hamming code word, it is so designed that the sum of the elements is still even, right? So S1, S3 and S4 and S5, all of them have been transmitted correctly, and by design the sum is of the elements in circle A is even. So if S2 is the wrong bit, then circle A still passes the test, but circle B and circle C fails the test. Okay? Similarly, if S5 is the incorrect bit, circle A fails. So let me just go one by one. So we have taken care of S1, we have taken care of S2. You can ask about S3 and S4. Well, if S3 is the erroneous bit and everything else is correct, then you can apply the same argument as we did for S2, because S3, just like S2, belong to 2 of the circles, and so B and C, and not belong to circle A. So exactly 2 of the circles and not belong to the other circle. Similarly, S3 also belongs to exactly 2 of the circles, A and C, and does not belong to the other circle, namely B. Similarly, if S4 was the erroneous bit, then S4 belongs to exactly 2 of the circles, A and B, and doesn't belong to the remaining circle, which is C. Okay? So the argument for S3 and S4 will be exactly similar for as we had for S2, and for S2 we saw that if S2 is the erroneous bit, then circles B and C fail the odd even test, circle A passes it. If S3 is the erroneous bit, then circle A and C will fail the odd even test, right? If S3 is the erroneous bit, then circle A and C, which are the circles which contain the element S3, they will fail the odd even test, while circle B will pass it. Similarly, if S4 is the erroneous bit, then circle A and circle B, which are the only circles which contain the element S4, they will fail the odd even test, and circle C will pass the test. Okay? So S2, S3 and S4 have similar behavior. So 2 of the circles will fail the test, and 1 of the circle will pass the test. Okay? Similarly, so the other case is when the error is in one of the last digits, last 3 digits, which is the parity check digits. So again, you will observe that the situation of S5 and S6 and S7 are similar. They belong to exactly one of the circles, one of the three circles, and not belong to the other two circles. So, for example, the element S5, the bit S5 belongs only to the circle A and does not belong to the circles B and C. So, if you make an error in S5, the circle A will fail the odd even test, but circle B and C will still pass the odd even test because none of the elements in circle B or circle C have been changed. Okay. Similarly, if you made an error in S6, then circle B only will fail the odd even test and circle A and circle C will still pass the test because none of them contain S6. Finally, if you make an error in S7, then exactly in the same way, circle C will fail the odd even test and circle A and B will pass it. Okay. So, exactly, so notice that we have gone over all the 7 possible bits where there could be an error, and we see that in each case there is a different combination of circles which fail the odd even test. So, here is how you can detect and correct a 1-bit error using the Hamming 7-4 code. So, as soon as you get the Hamming 7-4 code, and let me erase this again and oops. So, as soon as you get the Hamming 7-4 code word, what you do is that you form this diagram of 3 circles, 3 intersecting circles like this, and put the S1, S2, S3, S4, S5, S6 and S7 in the 3 circles A, B and C as in the picture. Once you do that in the picture, you check for each of the circles A, B and C, you check whether the sum of the bits in that circle adds up to an even number or not. And you observe which of the circles passes this odd even test and which of the circles fails this odd even test. And we just noted that depending on which of the bits between S1, S2 up to S7, depending on which bit is wrong, a different combination of circles will fail the odd even test. So, by observing which combination of circles fails the odd even test, you can determine which of the bits was erroneous, and once you figure out which of the bits is wrong, you just switch that wrong bit from its current status to the complementary status. So, if the current status is 1, you switch it to 0. If the current status is 0, you switch it to 1. Okay? So, you just change the status of that erroneous bit and you will get the correct code word. Okay? So, this is how you can not only detect, but correct a 1-bit error using a Hamming 7-4 code. Okay? Any questions? Any questions? Okay. So, so here is a table to summarize. So, if error is in bit S1, then all the circles A, B and C will fail the parity check. Parity check means odd or even. So, fail the test means the sum of the bits in that circle is odd. If the error is in S2, only B and C fail. Only if it is in S3, only circles A and C fail the test. If the error is in S4, only A and B fail. If the error is in S5, only A fails. Error S6, only B fails. Error S7, only C fails. And if there is no error, then all of the 3 circles A, B and C pass the parity check code, in which case you can declare that the code word has been transmitted correctly. So, from the table we can easily see that a 1-bit error can not only be detected, but also corrected by Hamming 7-4 code. Okay. Any questions? So, here is a example of a 1-bit error. So, assuming at most one error, find the original code word of the following Hamming 7-4 code words. So, you draw the 3 circles for A and for B, and notice and put the elements in there as shown in the picture here. and notice which of the 3 circles fail the parity check test. And in the first case, you will see that all of the 3 circles fail the parity check test. So, following from the wisdom received from the table, the error is in bit 1. So, you switch the bit 1 from 0 to 1 to get the correct code word. Similarly, for the second case, case B, only circles A and C will fail the parity check test. So, from the table, bit S3 is wrong. So, again you go to bit S3. So, here you change it to 0. So, this is the correct one, and you go to in a section B, in example B, you go to S3 and change it from 0 to 1. So, this is the correct one. Okay? Any questions? Okay, so now let us go on to the discussion of 2-bit error. So, suppose there are suppose you are looking at a Hamming code word and there has been errors in 2 bits. So, so if there are 2 errors, then there can be various possibilities, various combinations of possibilities. So, one kind of possibility is that error in S1 and one of S2, S3 and S4. So, error in S1 and one of S2, S3 or S4. Remember that S2, the situations of S2, S3 and S4 are kind of symmetric. So, let us just focus on S2. Or it can be error in S1 and error in one of the outlying bits. So, S5, S6 and S7, or it could be error in 2 of these ones, or it could be an error in one of these and one of those. So, one of the S2, S3 and S4 and one of S5, S6 and S7. Well, I mean, there could, in principle, there could be error in 2 errors among S5, S6 and S7, but the point is that you know, if there are errors in S5, S6 and S7, that means S1, S2, S3, S4 has been transmitted correctly, right? So, at least you have that. So, we will consider 2 typical cases. In one case, there is going to be an error in S2 and S5. Another case, there is going to be an error in S2 and S6. So, S2 and the bit in the same circle as S2, and S2 and a bit in the different circle than S2. So, these are the 2 representative scenarios in case 5, and the other cases are also there, first 4 cases. So, so in each case, it will be seen that at least one circle contains a single error and hence fails. So, so we will get into the details of that in a moment, but let us jump ahead a little bit and see what can we deduce as a conclusion from these considerations. We can conclude that Hamming 7-4 codes can detect 2-bit error, but it may fail to detect 3-bit error. For example, if S2, S3 and S4 are all wrong. So, for instance, so here is an example. So, here is an error which it cannot detect. So, if S2 is wrong, S3 is wrong, S4 is wrong, if all the 3 are wrong, then notice that in each circle, for example, in circle B, you are changing the status of both S2 and S4. So, it is like, so if the original sum was even, if you change the status of two of the bits, then it is like adding 2. Okay? So, if the original sum of S1, S2, S4 and S6 was even, and if you change the status of S2 and S4, then the final sum after the change is also going to be even, because you have switched 2 bits from 0 to 1 or 1 to 0. Okay? So the total sum will either remain the same, or increase by 2 or decrease by 2. Okay? So for instance, S1, S2, S4, S6 could be, let's say, 0, 1, 0, 0, and if you change the status of both S2 and S4, the sum remains the same. Similarly, if it was both 0, 0, and if you change the status of both S2 and S4, the sum increases by 2. Okay? Similarly, if it was both 1, 1, then the sum, then you would switch both of them to 0, so the sum would decrease by 2. So in both cases, in all cases, the sum, if you change 2 bits, the sum always changes by an even number, or it stays the same. And in both cases, and therefore in all cases, in the changing of 2 bits, S2 and S4, the original sum was even, so the final sum will also be even. So if you change all the 3 bits, S2, S3, and S4, then we just saw that for circle B, the sum remains even. Circle C, by the same argument, because exactly 2 bits, S2 and S3 are changing character. Therefore, for circle C also, the sum will remain even. And similarly, for circle A, only 2 bits, S4 and S3 are changing their character. So again, the sum will still remain even. So although you have changed 3 bits, S2, S3, and S4, the sum in every circle remains even and therefore passes the parity check test. Okay? So if you make error in detecting 3 bits, if you make an error in transmitting 3 bits, the Hamming 7/4 code fails to detect the 3-bit error. So let us go back. So 1-bit error was easy, 3-bit error, as we saw, was easy. Let's go back to the case of the 2-bit error, which is a little complicated because it has many cases inside it which need to be considered, as we saw here. So let us go back and try to see via example why the Hamming 7/4 code can detect these 2-bit errors. Okay? So we will address some of the cases, let's say a few of the 5 cases, and try to sort of understand how the Hamming 7/4 code can detect when you make errors in any of the 5 cases. Okay? So let's, for example, take the case 1, which is error in S1 and one of S2, S3, and S4. And notice that S2, S3, and S4 are symmetric in this diagram. So let's just, for example, let's take S2. So suppose you have made an error in S1 and S2. So these are the wrong ones. So S1 is wrong and S2 is wrong. Okay? So let's see if the circles pass the parity check test. Start with circle B. Does it pass the parity check test? Notice that in circle B there are 4 elements, S1, S2, S4, and S6, out of which you have changed the status of 2, S1 and S2. And we just discussed that if you change the status of 2 bits, then the resulting sum still remains even, right? So it still passes the parity check test. So circle B is okay with respect to the parity check test. Let's now go to circle C. Again, in circle C, you change exactly 2, S1 and S2, 2 bits are changed. So the circle C again passes the parity check test because you have changed the status of exactly 2 bits. Let's now come to circle 1. In circle 1, it turns out there is exactly 1 bit whose status you have changed. So then, as a result, the character of the sum of the elements in circle 1 will change from even to odd. So the circle A, the circle A therefore will fail the parity check test. Okay? So, right. So, so this shows that in case 1, you can always detect that there is an error. So, let us now go to case 2. In case 2, S1 and one of S5, S6 and S7 is wrong. So, suppose S1 is wrong and let us say S5 is wrong. Okay? So, S5 is wrong. Let us see if the circles fail the parity, pass or fail the parity check test. Let us start with circle A. In circle A, you have changed the status of 2 bits. Again, as we already discussed, if you change the status of 2 bits, the even sum remains even and therefore it still passes the parity check test. So, A is good. Let us start with B. If it is B, then already we have just one element S1 whose status is being changed. Just one bit flips the status from 0 to 1 or 1 to 0 and therefore circle B already fails the parity check test, because if you flip the character of one bit, then the even sum is converted to an odd sum. Okay? So, again, because one of the circles fails the parity check test, you immediately conclude that there must be something wrong. Similarly, let us take case 3. Error in 2 of S2, S3 and S4. And again, S2, S3 and S4 are symmetric. So, let us just take S2 and S3 which are wrong. Okay? Suppose S2 and S3 are wrong. So, these are wrong. If these are wrongly transmitted, then again for circle C, 2 bits change their character. So, even remains even and the circle C passes the parity check test. Come to circle A. Already you see that exactly one bit changes its character, namely S3. So, for circle B, so for circle A, the even sum changes its character to odd and therefore circle A fails the parity check test, and as soon as one circle fails the parity check test, you immediately raise an alarm that there has been a mistake, an error in transmission. Okay? And similarly, you can go on to with verifying the other cases. I will not go through the details of all of them in lecture, but you can convince yourself from this diagram that in each of these cases, in each of these possibilities, you will always be able to find out that there has been an error in transmission. Okay? Okay, so let us now dwell a bit more on 2-bit error. So, in case of 1-bit error, we saw that the Hamming 7-4 code can not only detect, but correct the 1-bit error. In the case of, and we also noticed that if the error is 3 bits, so if there are errors in too many bits, then the Hamming 7-4 test might actually fail to correct the error, might fail to even detect the error. Okay? So, in 2 bits, a 2-bit error, we just saw that the Hamming 7-4 code word is always able to detect that an error is there. Now, the question is whether it can correct it or whether it can pinpoint the error. So, there is a difference between detecting an error and detecting that there is an error versus pinpointing an error. So, pinpoint is the same as correct in this case, because you have just two statuses, two possible status, 0 or 1. So, if you can pinpoint that this particular bit is incorrect, I will just go and immediately flip the status of that bit from 0 to 1 or 1 to 0 and it will become correct, right. So, pinpoint is the same as correct in this setting. So, the question is, for 1-bit error, Hamming 7-4 code word both detects that there is an error and corrects it. If there is 3-bit error, it detects that there is an error in transmission. If there is 3-bit error, it does not even it is not even able to detect the error in certain situations. In the case of 2-bit error, it can detect that there has been an error in transmission. So this it can always do, as we saw in the last slide, but it might fail to correct the error, or it might fail to pinpoint where the error is. So let us see this through an example. So here are some examples of errors. So the red crosses. So for each of these domains, there is exactly 1 bit, right? So each of these domains represent exactly 1 bit, which you figure out from this diagram for the Hamming 7/4 code word. So, and a red cross means that there is an error in that particular bit represented by that slice. Okay. So notice that if there is an error in these 2 bits, then circle A is the only circle which fails the parity check test, because a circle which will fail the parity check test if there is exactly 1 error in that circle. If there are 2 errors in the circle, it will still pass the parity check test, because if you flip the parity of 2 bits, then even remains even, right? And the circle will also pass the parity check test if it does not contain any of the errors, like circle B. If it doesn't contain any of the errors, then the sum remains the same, so it still passes the parity check test. So there will a circle will fail the parity check test if there is exactly one error in that circle. And notice that in each of these three situations, there is exactly 1 error in circle A. So circle A fails the parity check test in each of these 3 cases, and circle B and C in all the 3 cases pass the parity check test. So only A fails the parity check, but the problem is that in these 3 cases, the errors have been made in different digits, different SIs. Okay. So in the first case, error has been made in S3 and S7, for example. So this is S3 and this is S7. In the second case, it is S4 and S6. This is S4 and this is S6, and so on. So this is S7. So you see that if there is a 2-bit error, then the Hamming code word can always detect that there is an error, because there is always a circle that is failing the parity check test, but it might not be able to precisely pinpoint which of the 2 bits are erroneous. Okay? So you won't be able to correct in the case of a 2-bit error, but you can always detect that there is an error. So the progression is as follows. So heuristically speaking, more and more complicated the error becomes, the less and less effective the code word is, as you would expect naturally. So if the error is of simplest kind, which is 1-bit error, then it always detects and corrects, and is able to pinpoint where the error is. So for 1-bit error, Hamming 7/4 code word can detect as well as correct. For 3-bit error, it might not even be able to detect that there has been an error. And for 2-bit error, so that's for 3-bit error, and for 2-bit error, it can always detect that there has been an error, but it might not be able to correct the error. Okay? Any questions? So let us discuss about another kind of error, which is erasure error. So suppose a Hamming 7/4 code word was sent, and the word received is so you receive a bunch of zeros and ones, but 2 of the bits are not clear what they are. Okay, but suppose the other ones, you know that they have been transmitted correctly. Okay. So there is no error in the transmitted word, except that the second and the fourth word are unrecognizable. So you don't know what they are. So such a fault is an erasure because it's as if you are erasing those bits. So you don't know what was actually in those bits. The question is, what is the transmitted word? And the answer is 1110001, because basically what you do is that, again, you go back to this picture, and you plug in the zeros and ones which are given to you, and then you know that every circle must pass the parity check test. So you just calculate the remaining 2 digits, whether they have to be 0 or 1, because every circle has to pass the parity check test. And if you want to do it in terms of equations, you can just observe that you need to satisfy these 3 equations. This is exactly equivalent to checking that each circle satisfies the parity check test, and you just plug in the zeros and ones which are given to you, and you calculate the remaining 2 digits which are not known from these 3 equations. Okay, you can do it either way, diagrammatically or via equations. So let us look at this bit more formally. So the erasure error, so some bits being unrecognizable involving at most 2 bits, can always be corrected. So you can always figure out the two question mark bits if there are at most 2 question marks. So if there are some bits which are unrecognizable and there are question marks, you can always calculate what they are, you can always determine what they are, as long as the number of question marks is at most 2. So how do you do it? Well, again, go back to the circles. So go back to the all important circles, and if there are 2 bits which are, wow, if there are 2 bits which are question marks, 2 unknown variables among S1 up to S7, the circles are set up in such a manner that there is at least 1 circle containing exactly 1 question mark. So we just solve for that, and once you have solved for the question or 1 question mark, you are just left with a system with only 1 remaining question mark, which you again solve in order to satisfy the parity check condition for all the 3 circles. Okay. So first you correct 1 error, because you will be able, there will always be exactly at least 1 circle containing only 1 erasure or only 1 question mark. So you first correct that error, that is determine that the value of that question mark, and now you are left with only 1 question mark remaining, and it is just a case of a single bit error, which you just calculate using the constraint that you have to that each circle must satisfy the parity check condition. Okay. Any questions? Okay, so if there are no further questions, then let us take a break of 10 minutes at this point, and when we are back, we will begin with voting and social choice. Okay, so let us now start with voting and social choice. So the motivating questions for us are as follows. So how do we choose a winning candidate in an election? Is there a perfect or best voting system? And so on. So before we attempt to answer these questions, we must figure out, or we must establish some standards for what does perfect or best mean. So what characteristics or desirable properties, in other words, do we want from a voting method? And is it possible to have all these characteristics? So the idea is that first determine some standards or some benchmarks, some criteria for which we want to evaluate our voting systems, and then try to find which voting system, if there is any at all, which satisfies all these criteria to the best extent possible. Okay? So here is a concrete example. So electing a class president. So suppose we must elect a class president. We assume that everyone in the class must cast a vote by writing the name of one of the candidates on their ballot. We need to choose a voting method, a social choice function. So voting method is often called a social choice function. That is, and in summary, this is a method which selects a winning candidate, or if you are in certain situations, if you want multiple winners, winning candidates, given the votes of the class. So if I give you the tally of who voted, so if I give you the information of who voted for whom, then from this information you will assimilate all this information and spit out a winner. Okay? So that's the social choice function or a voting method. So which method should we use to pick the winners and why? So the following issues may come up. So normally one might, a natural thing to do is, and probably this is the thing that we do in most cases, is to pick the candidate with the most votes. Okay? But the question is that, is it necessarily the best way always? Next, there is a question of, suppose the top two candidates get the same number of votes. So in some sense there is a tie. So what do you do? So one solution might be to drop one of the votes. And so then the two candidates might have different vote counts, and one will be a winner. Or you could, this is also done sometimes in practice, that you toss a coin if there is a tie and decide the winner based on that. Or you can just declare both the candidates as jointly winners. So that's also possible. So and what if one of the candidates decides he wins no matter what? Okay, so he is the strong man, and he declares himself the winner no matter what anyone else thinks. So for example, in this classroom, if I declare that I am the winner, I don't think too many of you will object, right? So what if we, so here is, so in addition to these possibilities, we can also introduce some more difficult or more complicated possibilities. So one of these, just to give you a flavor of what a more complicated voting scenario might look like, what if we can ask the question as to what will happen if you weighted different students' votes differently. Okay? So these are very pertinent questions, and we will see, every question has its own rationale, and they have been asked at various points in history, and there are certain ways to deal with these situations or these scenarios. So that's all. That's what this topic is about. So as you might imagine, this is voting and social choice has been a very very hotly debated topic in history, and there are many quotable quotes here. So we would like to emphasize that the lectures are actually not about politics in that sense. Instead, they are only about the following. So, once everyone, all the voters cast their votes, what is the best way to determine the winners? Okay? So, whether or not to vote is a different matter. What we are interested in is that suppose everyone has voted, now what is the best way of aggregating all the information carried by the individual votes in order to spit out the best possible winner. Okay? So, that is what we are interested in. So, here are certain quotable quotes in the theory of voting. So, one of these quotes is that it is not the people who vote that count, it is the people who count the votes, for obvious reasons. So, the art of counting the vote is exactly the art of combining the aggregate voting information of all the voters and spitting out the winner in the best possible manner. And I care not who casts the votes of a nation, provided I can count them. So, in some sense, it is about being oblivious to the identities of the specific votes. It's only about which candidate receives how many votes, instead of exactly who is voting for whom. Okay? So, it's kind of two different scenarios, because so for instance, so suppose there is a certain candidate and you might vote for him, but I might not vote for that candidate, right? Now, there can be certain situations where it might lead to a different result if you vote for him and I don't, versus I vote for him and you don't. Although in both cases he gets one vote, right? So these kind of this kind of situations have also been considered in history as to whether it is important to recognize the identity of the votes, or whether it's a good idea to be oblivious to the identity of the votes. So as long as the same candidate gets 10 votes, it doesn't matter which are the 10 votes, which are the 10 voters who voted for him, right? So that's being oblivious. So, so let us go a bit further and introduce some notions to make things concrete. So, we begin with the case of two candidates, A and B. One candidate elections are not that interesting because you don't have much to elect, right? And the other point is that candidates need not be people, they can be choices. So, for example, this often happens in the case of referenda. So, yes or no, okay? So, we assume that all voters submit a ballot with either A or B and not both, because in that case the vote will be invalid. So, either you vote for A or you vote for B, and the collection of all ballots is called a profile. So, for example, this is a profile. So, these are the voters 1, 2, 3, 4, these are the various voters and these are their choices. So, first voter votes for A, second voter for A, third voter for B, fourth voter again for A, fifth voter for B, and so on. Okay. So, social choice functions. So, a social choice function or a voting method is a function which takes in, whose domain, or which takes in as argument the set of all possible profiles from a fixed electorate. So, for example, you can feed in this particular voting profile into the voting system or the social choice function, and its codomain or output. So, domain means just input here, and codomain, by codomain we just are dealing with the notion of output. So, you input a voting profile and your output is either A wins or B wins or a tie. Okay. So, these are the only three possibilities. Oops. So, these are the only three possibilities. So, either A wins or B wins or it's a tie. So, a voting method or a social choice function is a function into which it's like a machine or a black box into which you feed the voting profile that you have collected from the election or the cloud voting, and the output is either A is the winner or the output is B is the winner, or the output is there is a tie. These are the three possibilities. So what is a non-example? So what is a non? So you might think that this kind of anything goes, right? This is too broad a concept. So here is a non-example to dispel your notion. So a non-example is, suppose we were to pick a candidate by flipping a coin. Say if the coin falls heads, A wins. If the coin falls tails, B wins. Is this a voting method? Is this an eligible voting method, or is this an appropriate social choice function as we have just defined it? The answer is no, because it doesn't take into account the profile of votes, right? So if you feed in the same profile of votes, if the coin is independent of the voting profile. So if the voting profile for the same voting profile, if the coin is heads, A will win. For the same voting profile, if the coin is tails, B will win. So for the same voting profile, you can have two different outcomes. So this is not an eligible voting method. Okay. So this method could pick different winners for the same profile, and this sort of probabilistic methods are not allowed. So here is a simple method, simplest voting method perhaps. This is a simple majority method. The simple majority method is the social choice function that, given a profile as an input, a profile means a voting profile, the output is the candidate with the most number of votes, and if the two candidates have the same number of votes, the output is a tie. Okay? So this is simple majority, the simplest method you can think of if there are two candidates in the election. So for a given profile, the candidate A wins because A has 3 votes and B has 2. Okay? So here is another example, tabulated profile. So observe that the simple majority method depends only on the number of votes cast for each candidate, not who cast them. Right? So this goes back to the quote of I do not care who votes in the election of a nation as long as I can count them. Right? So it doesn't matter who votes for the candidates. All that matters is the vote count for each candidate. So for the simple majority method, really all that you need to know is the tabulated profile, not the actual voting profile. The actual voting profile contains the information of which voter voted for whom. Whereas the tabulated profile just is collecting the total number of votes for each candidate and into a table like this. So there can be other methods than the simple majority. So an example is the super majority. So for example, if P is a number between 50 and 100, the super majority method with parameter P says that whoever gets at least P% of the total votes wins and a tie otherwise. So let's say P is 51. So if we calculate we tally the votes for each candidate, and if there is a candidate who receives at least 51% of the votes, then he is declared the winner. But if no candidate receives 51%, so for example, both candidates might receive 50, or it might be so that one candidate receives 50.5, the other candidate receives 49.5, right? That's also possible. In that case, there is a tie. So although the candidate who got 50.5% of the votes got slightly more votes than 49.5%, which is the votes of the other candidate, still by the supermajority method, the result is a tie because we want at least 51% to declare for the candidate to be declared a winner. Otherwise, it's a tie. Okay? So an example of this is an extreme example. So when P is equal to 100. So you need 100% of the votes, only then you can win, otherwise you do not win. So in other words, the candidate can only win by a unanimous vote. Everyone must vote for the candidate to win. So this is what happens in a jury trial, because the jury must agree on the conviction. Okay? So here is another method, which is the quota method. So let q be a positive integer. So the quota method with quota q chooses a candidate with at least q many votes and tie if more than one passes the quota. So you select a threshold of votes, and any candidate who clears that threshold of votes is declared the winner if there is only one candidate who clears the threshold. If there are multiple candidates who clears the threshold, then the result is declared to be a tie. Then there is the method of status quo, which is implemented in the following way. So one of the candidates is designated as a status quo and the other as the challenger. So now use a social choice function, for example, simple majority or super majority, to first determine if there is a unique winner, and if so, select that winner. If not, we select the status quo. So one of the candidates is declared a status quo candidate. So this is kind of the sort of the default choice in some sense. So what you do is that first you use a simple method like a simple majority, simple social choice function like simple majority or super majority or one of the other methods that we have studied, and apply that method, for example, simple majority, to the voting profile. Okay. If that method spits up a unique winner, then you are happy, well and good, you just go home with that winner. If the simple majority method, for instance, fails to throw up a unique winner, so for example, if there is a tie, then you fall back onto the status quo candidate. So you always declare a winner. The only difference with simple majority is that you never declare a tie. Instead, when there is a tie in the simple majority, you declare the status quo candidate as the winner. Okay? So there are other voting methods. So this is the weighted voting method. So weighted voting method. So suppose there are n voters labeled 1, 2, 3, 4 up to n, and voter I is given a positive number wi of votes, and so the total number of votes is the sum of all the wi's. So this method selects the winner among the two candidates A and B. It selects a candidate who receives more than half of the votes. Okay, so at least T over 2. If no such candidate exists, the result is a tie. So in this case, every voter has a vote, and in principle the influence of two different voters may be different. So this is the difference with simple majority, where the influence of every voter is the same. All voters are kind of treated equally. Here all voters are not treated equally because they have different votes or different weightages associated to their votes, or in other words, every voter has a different number of votes. Okay? So the voice or the opinion of different voters matter to a different degree. So for example, in 1994, Mr. Lee Kuan Yew suggested giving 2 votes to citizens aged 35 to 60 married with children. Okay? So these are kind of voters to whom kind of they were, it was considered to accord them more importance because of their situation in the society. Okay? Dictatorship method. A particular voter is chosen to be the dictator, and the winner is whichever candidate the dictator chooses. So really in this class, for example, if there is a voting and you vote and I vote and maybe I am the dictator, and no matter who you all vote for, I will pick the winner, and the candidate I point to is the winner, and your votes do not matter. Okay? So that can be also a way. Probably it's not a nice way, and probably it's not a way that we want to implement, but that's one way, right? For example, everyone votes, but only Vladimir's vote counts. Monarchy method. A particular candidate is chosen to be the monarch and is the winner regardless of the votes. So again, there is a specially designated candidate, and no matter whoever else runs in the election, or whoever, no matter who the voters actually vote for, the monarch is always the winner. Okay, that's also possible. Again, might not be the best best solution, but one solution. Simple minority method. The candidate with the least number of votes wins, or a tie if both candidates get the same number of votes. So, of course, this is useless because, why would you go for a candidate who no one supports, but okay, I mean, it satisfies our definition, because if you feed in the voting profile, it will spit out a winner. It will look for the candidate who has the smallest number of votes and spit out that candidate as the winner. Of course, but for practical purposes, it's useless. And you can define many other, you can come up with many other methods which perform the simple function of taking in a particular voting profile and throwing up a winner A or B or a tie. Okay? Okay. So, there are many possible desirable properties of the voting methods against which we want to evaluate our voting systems, namely anonymity, neutrality, monotonicity, and so on. Some of these words might sound complicated, but they are actually very natural and logical propositions when we get to them. But we will get to them in the next lecture. So, for today, this is where we will.